All right, well, we're talking about support vector machines today. Um, I really, I'm always torn about this topic because support vector machines are a less commonly used technique. So they're a machine learning algorithm that isn't commonly used, in large part because there's usually a better thing that you can use. But they nonetheless come up a lot during interviews, and I'm happy to talk a little bit about why I think that is. I think it's actually for historical reasons. But the upshot is they're helpful things to know about for interview purposes, even if they don't, you're not going to see them winning any Kaggle competitions. You're not going to see them whipped out as a class of particularly interpretable model. They have a lot of important limitations. But for historical reasons, they're popular. So in the late 90s and early 2000s, when support vector machines became a thing, there weren't that many options for people who wanted to do machine learning. There weren't that many algorithms you could use, partly because the technology just wasn't there. The compute cycles weren't there to build neural networks, or at least to make neural networks effective. And people hadn't realized how to make neural networks in the way they have now. Ensemble learning wasn't what it was. Tree-based models weren't what they are. So anyway, these things have been superseded by a lot of different things, but they were mathematically elegant, and that led the mathematics community to really seize on them, and that's kind of the history behind it. And so the actual math behind it is somewhat complex. It's quite interesting, but somewhat complex. So what my hope today is to walk you through the intuition behind it, so you know functionally how these things work, and you can answer interview questions about them. So I want to start with a one-dimensional support vector machine, which will seem a little bit pointless at first, but hopefully you'll see how this evolves somewhat seamlessly into the full sort of high-dimensional case. So what we're going to imagine here is that we have two clumps of points. So we've got red points and blue points. We're imagining a classification problem. And what support vector machine is going to do is it's going to try to identify what the best border is between these two sets of points. Now that's actually, as a general rule, I mean that's what all machine learning algorithms really do. They try to define some decision surface, some border between sets of points. And so what differentiates them is the rule structure that they use to establish what's going to be on one side of the barrier and what's going to be on the other. And so in this case, the rule structure is pretty simple. What we're going to do with a support vector machine is we're going to maximize what we call the margin. So the margin is the space between the closest point of one class and the essentially the midpoint to the closest point from the other class. So we're going to try to set up a margin, a sort of bisector along this axis that maximizes the margin between these points. Pretty intuitive, at least in 1D. It seems almost so intuitive that it doesn't even need to be mentioned. But this principle we'll see extends to higher dimensions quite easily as well. So this thing, I mean, it's referred to as a maximum margin, sort of. Yeah, so yeah, Laura, like you're right. I mean, you could think of it as, that's right, splitting the difference. That's it. So in one dimension, you're really looking at that bisector. In fact, you're right. You're literally splitting the difference, at least in 1D. And we'll see. In a way, you could still make this case in higher dimensions, but it just gets a little fuzzier. But we'll see how that all maps on. So yeah, for now, Laura's sort of split the difference analogy is a good way to keep that in mind. Now, right, so this is a contrived example. And as happens a lot, when you want to describe something like a machine learning model, you usually use a contrived example to motivate it, and then somebody comes along and shows you something annoying like this. So in this case, we're using the same rule. We have blue points and we have red points, and we add this maximum margin classifier. But you can see there's a problem because we've got this red point here, and it just happens to be really close to the border with all those blue points. Now, it doesn't seem as if this red point particularly represents the bulk of the red points, because the bulk of the red points are back here, and this guy's just like an outlier. But one outlier is all it takes in this case to move the margin way over to the edge, to the point where now this classifier, I mean, you could argue is somewhat misleading. I mean, it's really giving you a decision surface that seems very much skewed towards towards the blue side. Really, it's classifying a lot more things as red as maybe it should. And so there's something not quite ideal about the way that support vector machines deal with these kinds of outliers. And so the solution is to use what are called soft margin classifiers. And this is basically just a forgiving kind of support vector machine. It's one that, yes, recognizes the fact that there's a point on one side of that boundary, but essentially is looking to optimize a more mathematically complex quantity, but ultimately in terms of the feel of it, it is roughly the same thing. It's not a hard margin classifier. So this, where is it? This is a hard margin classifier where you're just absolutely insisting that you will get that border or clearly separating the two classes, and this is a soft margin classifier. So one thing you can tell immediately, and there's a parameter that controls how hard your margin is if you're going to train a support vector machine in scikit-learn. And I want to tie that parameter into a concept that you guys probably all know about, and this is the idea of overfitting. So in this particular case, when we have the hard margin classifier, and the boundary is essentially fully determined by the closest 2 points, right? So these 2 points are the only points that matter. When that happens, we're at high risk of overfitting, right? Because really what all we'd care about is like these 2 points, and they're defining the entire decision surface. So a hard margin in general will tend to overfit more than a soft margin. A soft margin is more robust. So this is when you're doing hyperparameter tuning with your support vector machine, the parameter that controls the hardness of that margin is really doing a lot of work to help you avoid overfitting or avoid underfitting as well. So anyway, those are, I guess, some tie-ins to maybe concepts you'll be more familiar with. So this is all in the one-dimensional case. We have hard margin and soft margin support vector machines. And of course, the cost with the soft margin is that, yeah, sometimes you're going to misclassify points. And so how do you know how many misclassifications to allow? In other words, how do you know how lenient to be with your margin? Well, the answer, of course, is cross-validation. And that's basically the same answer that I would have given with any other hyperparameter optimization process. There's no way to know how hard that margin needs to be. You have to try it with your training data, and then you have to try it with your validation data and see what minimizes the validation loss. I just want to pause there now that we've explored the 1D case a little bit. Does anybody have any questions about the 1D SVM? Cool. Here, Laura, I'll pick on you because you had that insight earlier. Do you have any specific questions about this so far? Nope. All good. All right, great. Perfect. So let's up the dimensionality here to get into some more interesting takes on this problem. Here's a support vector machine in 2 dimensions. Again, we're playing the same game here. We want to come up with, this time, instead of just a point that separates points along a one-dimensional axis, we want to come up with a line that separates points in a 2-dimensional plane. Okay, so the dimensionality of this border is always going to be 1 dimension less than the dimensionality of the data. So what I mean by that is you can see in this case we have, just like before, we do have a margin, right? So we have this like ideal kind of line, and it's always going to be a straight line that the support vector machine builds. It's a straight line that basically bisects our data, and we're trying to basically maximize that margin. And in this case, I'll zoom in just so you can see, this margin here is defined in this case like not only just by 1 red point, but actually by 2 of them. So you can actually have, just by coincidence, 2 points that happen to be exactly equidistant from that line. And in that case, they're both going to basically determine that line together. But if one of these points was closer, then the line would end up having to shift to maximize the effective margin. So essentially, this is like if we were to try to rotate this line, you can sort of see how any amount of rotation here is going to reduce the space, either on one side or another. So let me just try to maybe illustrate that with a little rotation here. So if we do that, right, now maybe it's less obvious, but you can kind of see the margin is reduced here and expanded here. And we care about the smallest margin, right? So we want to maximize the smallest margin here. So we actually, and this kind of thing just makes it even worse, right? So we don't want any of that. We want to stick to something like that. Okay. So that's the name of the game in 2D, is basically like, how do you come up with a line that's going to bisect your data in a way that maximizes that margin? That's the essence of the support vector machine. Cool. So this is all well and good if you have, again, a contrived example where your points are well separated, right? At the moment, you can clearly see, there's a pocket of blue points, there's a pocket of red points, and it's pretty straightforward. I draw a straight line, and then conveniently, one set of points ends up on one side and the other on the other. But that's not always the case. You could have a situation like this, for example, right, where we've got that red point right in the middle. How do you bisect that with a straight line? You can't. And that's actually a situation where a cookie cutter support vector machine will start to fail. And I want to kind of flag or highlight the way that failure mode is avoided. So let's look at, again, the simpler 1D case. Go back to 1D. So here's our problem, right? We have a single cutoff that a support vector machine gives us. In the case of one-dimensional data, we get 1 point that we can split our data up. And there's no place here where you can do that and end up with all the blue points on one side and all the red points on the other, right? If we put a line, say here, we would end up with all these red points here, and sure, all the blue points would be on the other side. Then you got these two stragglers, these two red points over here. And likewise, if you put the border here, you've got a whole bunch of blue and red on the other side. So we can't get pure class separation when we have data that looks like this. And in general, data will look like this because the world is a dirty place. So we need to find a way to fix this problem because it's, of course, completely unsatisfactory to have a machine learning model that works fine as long as your data happens to look like that, but then completely fails the minute anything remotely looking like the real world problems start to surface. So how are we going to do that? Well, I want to introduce you to what's known as the kernel trick with the support vector machine. And here's what we're going to do. Our first step is going to be to define a new axis. Okay, so what I did was I took these points, I moved them down, and boom, there's just a new axis. We're now going to come up with an arbitrary function. Okay, totally arbitrary. Let's call it y equals x squared. And we're going to place these points in a location on the y-axis that's given by this formula. Okay, so let's say we've got a red point that's at position. Let's call that x equals 2. Then its y-coordinate will be y equals x squared will be y equals 2 squared or 4, and then maybe this is 3. X equals 3, so we'll move that up to 3 squared, which is 9, and so on. So we're going to basically make a quadratic curve out of these points. Here's what that's going to look like, something like this, right? So all we've done is we've taken whatever their x coordinate happens to be, and we do x squared in this case to give it a y value. Okay, so this is just as an example. We happen to be using y equals x squared, but we could have used anything else. But we're gonna do this and see where it takes us. So what's interesting now is that we have a two-dimensional problem, right? A moment ago, when we were looking at this is our same 1D problem that was causing all those problems. Like, how do you separate that cleanly with just one separation? You can't. But now something interesting is going to happen. We can actually separate the blue lines from the red lines with a single straight line. And the reason is that there's this curve now in the data. So here's what that would look like, right? I'll just zoom in so you can see that, right? So we now have this one straight dotted line that is, in fact, perfectly separating all the blue points on one side and all the red points on the other. So really what we've done here is we've invented a new axis, and we mapped these points onto that axis using some arbitrary function that essentially created an opportunity to then cut the data in two, right? So that's actually this is called the kernel trick, and this function y equals x squared, the one that we happened to choose this time, though we could have picked something else, is called the kernel function. So this is the kernel that is used to project a one-dimensional problem into 2 dimensions. Now, oh yeah, okay, good, that's what actually now I want to pause here just because I think this is the conceptually most challenging part of the support vector machine saga. Does anybody have any questions about this? Maybe I'll pick on the odd person here. James, does this work for you?
Yeah, I think so. I might come back in a few minutes and follow up, but so far I think this makes sense.
Okay, and Dustin,
Yeah, so I, I hear the word kernel and I know it means something else in machine learning. So I'm sort of eager to see where this is going.
Okay, sounds good. Hopefully you're satisfied by the by the end destination here. Okay, but the idea is okay. Okay, I'll take that as a yes. Yeah.
Yeah.
Okay,
Yes. Yes.
awesome. Great. So that's the essence of this kernel trick. What we're going to do is take our data, which is completely non-separable in a lower dimension, for example, 1 dimension, and we'll promote it to 2 dimensions using some arbitrary function. And the hope is that if we pick that function correctly, we'll end up with something that is separable in that higher dimensionality. Now, what's interesting here is the more you do that, the more dimensions you add. The more dimensions you add, the more chances you have to end up with a separable problem. And so, if our problem wasn't separable in 2 dimensions like this, we could have done this again. Right? We could have said, okay, fine, we'll create another axis, the z-axis, and now we'll use, I don't know, z equals sine of x plus y or something, or whatever it is, to get another shot at separability. Now, you could eventually overfit by doing this, of course, because you could create 1 dimension for every point, and that wouldn't be very useful. But just to illustrate the basic premise, the point here is support vector machines get more and more likely to successfully be able to separate the data out using a straight line or a point or a flat plane the more dimensions you give them. So in fact, this is where we're deriving here one of the key properties of the support vector machine, which is that they tend to perform best in high dimensionality, low data settings, low sample size settings. So the higher the dimensionality, the more excuses, the more opportunities you'll have to fit that plane. And that's really what we're doing here is in a way, you could call this feature engineering, right? I mean, we're creating a new feature that we're calling y that happens to be x squared. And if you're used to working with linear machine learning models that make assumptions of linearity, like, for example, logistic regression, you know that sometimes you have to do this because logistic regression can't work with it can't detect nonlinear correlations in your data. So sometimes you have to create features with nonlinearities so that logistic regression can actually then anyway use them to make predictions. So anyway, bottom line is this is a kind of feature engineering in a way that creates an opportunity to find a bisecting planar line. But this also works in higher dimensions. And I want to show you a particularly common example that people like to use.
We have somebody in the comments who made an analogy to reverse PCA.
Sweet. Okay, thank you, Dustin. I really appreciate it. Otherwise, I miss these things. So Gorang, you were saying, this theory is like reverse PCA, where instead of reducing dimensions, we increase dimensions so we can classify it. In a way, there are of course some differences in terms of the goals here, but we certainly are. When we do feature engineering, I guess the analogy here is somewhat involved, but in a way you can think of it just in the sense you're adding more features as a kind of reverse PCA. Here's an example from 2 dimensions to 3 dimensions, just to anchor in. So keep in mind, this is actually the same thing as what we did here, but we're now going to do it in higher dimensionality. So let's take a situation like this, where if you tried to fit, let me just do some impromptu keynoting here. If you tried to fit a straight line that bisected this to capture all the reds on one side and all the blues on the other, that is not going to happen for you, right? It doesn't matter how you rotate this border, you're just always doomed to failure, right? But you can clearly tell, looking at this data set, that surely there's got to be a way of cleanly separating these two sets of points. And this is where the kernel trick is going to come in. The kernel function that's going to work really well here is something that gives you a lower value in the center and an increasing value as you move to the outside, something that basically gives you like a bowl shape. So if we use the function z equals x squared plus y squared, essentially what this does is it's like a parabola that's coming out in the x and y dimensions. We'll end up with something like this. So I just want to illustrate this with a couple of quick examples. So imagine we have a point close to the inside here. It's got, you know, like a pretty low, it's got a really low y value and a relatively low x value. So the z value is going to be quite small, right? X and y are both small because we're close to 0, 0. And so z is going to be small, so we'll end up low down here. This thing here is the z-axis. So we're here, where these blue points are. But as we move further away, we end up with either high values of x or high values of y. And as a result, you know, x squared plus y squared is going to be pretty big. And that's why we end up with these points up here. Now the exciting thing is that now that we've done this, now that we've created this new axis, you can find all those red points up here, all those blue points down here, where they can be bisected with a plane. So now we can have a clean slice, a straight level plane that goes right across and cleanly separates the red from the blue. So essentially this is the exact same process as what's happened here, right? Where here we were able to cleanly bisect thanks to the promotion of these points to a 2D environment from a 1D environment. And we're doing likewise here. We're promoting from a 2D environment to a 3D environment, and thanks to the kernel function being the right kernel function, we ended up with something that was separable. We could have failed, though. It is entirely possible that we could have picked a kernel function that just did not work for the job. And if that were to happen, we would end up needing a soft margin classifier. We would end up being more at risk of overfitting. We might need to just try again with another dimension. There are a whole bunch of sort of downstream effects that come from that. But this is what we're going for philosophically. We're trying to hit the nail on the head with like a one-shot kill, basically, where we just get that kernel function just right. Which raises a second point. So I talked about this idea of the margin. The margin in the support vector machine being this key hyperparameter that you can tune. The harder the margin, the more you're overfitting, and the softer the margin, the more robust you're going to be to overfitting. The more you're underfitting, really, at risk of underfitting. This is another hyperparameter choice. What is your kernel function? Are you going to use a quadratic kernel, right? Like z equals x squared plus y squared, or actually I think coincidentally I happen to use a quadratic kernel here too. It's just in a lower dimension. You know, y equals x squared, or are you going to use a sinusoidal kernel, you know, cosine or sine of x plus y or whatever it is, or are you going to use something completely different? And an example of this is, or one very common kernel is what's called the RBF kernel, and this is essentially a Gaussian kernel. What this does is it transforms your data using something like e to the minus x squared, I think it's e to the minus x squared, e to the minus x squared plus y squared, something like that. I'm embarrassed to say I don't remember the exact formulation, but something like that. And it turns out that this gives you actually a very limber, very fluid, very shapeable decision surface that ends up working very well in practice for a lot of applications. So it's one of the default choices that you can make when you train a support vector machine scikit-learn. You can choose the RBF kernel, you can choose a linear kernel, or you can choose a quadratic kernel, and so on and so forth. So all these options are available to you. You won't know in general which one works best until you try it on your validation set. And you can even specify custom kernels. I think if you want to get really fancy, I believe scikit-learn actually lets you define your own kernel functions and feed them in if you want to kind of crack things open. But most of the time, people don't tend to do that. Cool. So are there any questions about these kernel functions or the kernel trick that anyone has?
Yeah, Jeremy. So on this 2D to 3D example on the screen, could you just give me an example of what these points might be? So let's say like you've got two species of animals, and these are like heights and weights and something like that. I'm trying to picture like what we're actually predicting, and does that mean that you can only really tune on one parameter? Like you can't pick like these three columns. It's not like a decision tree where you can just customize. It seems like you're pretty limited to just whatever these values are.
Yeah, you're right that there's really something. Trying to find the right word here. There's something hard coded about this kernel function. Something a little inflexible and haphazard about it. You're absolutely right. So I will make this a little bit more concrete. I think that's a great idea. So let's take a look at our data set here that has these two concentric circles. I'll try to imagine something that would make sense here. So let's suppose, okay, good. Yeah, let's, wait, no, that's not quite going to work because those can't be negative. Yeah, it's tough because I got to think of an example where something can be negative too. I don't know. Let me know, folks, if you think of anything that fits the bill. I was going to say, because James, you mentioned arm span and height, and like that, you could use stuff like that, except it only applies to the positive end. Anyway, let's imagine it's that for now. So, you might have what a shape like this implies, and it may not be immediately obvious, but what a shape like this implies is that you have a certain conserved quantity. It seems as though, for the blue group, the sum of x squared and y squared is never bigger than or less than the square of this radius, right? So I'll maybe a quick lesson in geometry. So the equation of a circle is x squared plus y squared equals constant. So if x squared plus y squared are always equal to a fixed number, then what you've got is essentially just the equation of a circle. So if you solve for y is going to be the square root of whatever that constant is minus x squared. That ends up mapping out the equation of a circle. And so anyway, sorry, I'm just trying to, so tying this into the physics of it is a little bit harder. But anyway, what this means is we have some combination of arm spans and heights such that they always fall in the circle. It's like, okay, cool, maybe x is arm span, y is height. And but now we want to separate them, so we invent this new feature z that's like x squared plus y squared. So maybe it's it maps onto something. The thing is, in order for these things to be physically separable, like to be separable in this way, this is a big hint that whatever z is, it actually has some physical significance. Like it's not a coincidence that that these large numbers of points are perfectly separable with a plane when we move it into this higher dimension in this way with this kernel function. So this is actually quite a conspiratorial thing. Like we found the exact right kernel function to make the separability show up. I'll think of some example that'll work with this kind of data, but it's sort of hard to on the spot.
But just to push the point a little bit, so if they're that separable, there's some feature z or something that's causing this, but we're only talking about heights and arm spans. If we have 6 or 7 other features in our data set, wouldn't we want to use an algorithm that actually brings them into the fold?
Yes, absolutely. So this is, you're right. We're pretending here that we have literally a two-dimensional problem. So like the only data that we have is arm span, height, and the color, the class that they belong to. In general, because I can't plot, I can't show you a 3D plot that we then upgrade to 4D because I can't plot 4 dimensions on a keynote slide. This is ultimately the best we can do for illustrative purposes, unfortunately. Does that make sense?
Yeah, okay. So support vector machines can work with all of the variables in just like a decision tree, you can bring all the variables in different ways.
Correct. Yes.
Okay, got it.
Yeah, and actually, I think that is a weak spot of the way I've been explaining this. We did a 1D problem, and now I'm showing you a 2D problem. This can be generalized to arbitrary dimensions. It's just that then this plane becomes a hyperplane, and these points become embedded in even higher dimensions. So yeah, that's all that happens, but the logic is still the same. You're always creating a new dimension creates new opportunities for bisection by a plane. And that's the essence of the kernel trick. The more dimensions you create, the more opportunities you have to slice your data. But you can overdo it. It's always possible to add too many dimensions and then to start overfitting. And then once you get to the point where you have a dimension for each data point, well then, yeah, like no surprise, you're going to be able to separate it from all the others, but you haven't really learned anything meaningful. So this is, in a sense, it's like another way of, another hyperparameter to think about is like how many dimensions should I add? So yeah, I hope that makes sense. So with that in mind, I want to take a look at something that very few people understand when it comes to support vector machines, and that is how feature importances work for support vector machines. Because you can actually, like if you go into sklearn, you will find a feature importance score for support vector machines. Most people just kind of like use it naively without thinking about what, how or what it means or how it works. And so I just want to give you a quick intuition as to how that works as well. So here we have a collection of points, and those points, they have their margin here. Sorry, there we go. Okay, and let's start off by imagining that they look something like this. Okay. Does anybody want to hazard a guess, just based on intuition, which feature here is the most important in determining class? So sorry, I should be clear. By one feature I mean x here, the x-axis, and then we have the y-axis, which is feature 2. So feature 1 x-axis, feature 2 y-axis. Can anybody take a guess as to which feature would be the most important as a determinant of? I'll put it another way. Which feature, which value, either x or y, if I give it to you, will be most useful in predicting the color of a point? Same. Do you have any thoughts? Or Mark, I don't know if you have any thoughts either. Okay. All right.
Yeah, we have a couple comments that conflict with each other here.
Oh, sorry. Okay, great. Cool. So yeah, Laura says. Oh, sorry. Actually, Laura's got another comment here. So it looks like an idealized perceptron hyperplane, and the perceptron also works better in higher. Yes. I would have to think harder about the analogy there, but there are papers that are published that show a deep equivalence between support vector machines with a linear kernel, in other words, without a fancy kernel, and logistic regression. And logistic regression is intimately linked to the idea of neural networks. It's almost like a zero-layer deep neural network. And so the perceptron, anyway, I think your brain is latching onto something actually quite fundamental there. Though I'd have to think about it some more to not say something stupid. And then Dustin says, oh, sorry, yeah, great. And then, okay, so we have a conflict between, so Laura's saying feature X, Suvik is saying feature Y. So Suvik, I'm sorry, but it actually is X. So here's the way to think about this. If I gave you the value of X, so let's say, I don't know, let's say this vertical line here represents X equals 1. So X equals 0 is here, X equals 1 here is, and X equals 2 is there. So if I tell you that X is greater than 1, immediately you know the point is blue, and if I tell you that X is less than 1, immediately you know the point is red. So X is super useful in terms of allowing us to predict class. If I tell you that Y is 1, let's say that's around here, that doesn't really tell me much about the classes because they're not separated along Y. So X is the most important feature here. Now, if we were to rotate this like that, now all of a sudden, if I tell you Y, if I tell you Y is greater than 1, then boom, you know it's red. If I tell you Y is less than 1, then Y is, then the color is blue. So there's something deep that this is telling us about the slope of this line, right? So if this line has a slope that's mostly directed along, let's say in this case, directed along the x-axis, then it's telling us that y is the most important variable. And likewise here, if the slope is mostly directed along y, then it's telling us x is the most important variable. If you go somewhere in between, right, something like this, then they're kind of both equally important, right? If I tell you the x value, okay, well, I guess with the way these points happen to be rendered, that's a little harder to see, but I don't know, something like that. If I tell you the x value, yeah, that gives you a little bit of information, right? Because if the x value is really high, then probably we're a red point, right? The red points tend to be further along on the x-axis, but not always, right? We have a couple of blue points that overlap with red points here. And if I tell you the y value is really high, then again, probably it's a blue point. But if I tell you the y value is low, now you're still kind of confused. So these two features are equally important when the slope is about equal to 1, when you have about a 45-degree angle there. So the slope of this line actually gives you a good indication as to feature importance. And that's exactly what's going to happen when you look at the feature importance scores for support vector machines in scikit-learn. That's how it's calculated, is based on the slope of that line. Anyway, I hope that makes sense. And as Suvika, I just want to check in with you, especially just to make sure that you're cool with that explanation. Does that work?
Yeah, exactly.
Okay, awesome. Great. So that at a high level is your support vector machine. You'll notice, by the way, that one challenge with support vector machines is that when you start inventing new features, right, in order to achieve the separability, you're kind of like now you're going to have, this line is going to have to involve a new invented feature. And the problem with that is it makes interpretability harder, right? Because when you ask for feature importances, you're not asking about the features that were engineered under the hood. You're asking ideally about the features that you initially put in. And so the support vector machine, when you start using fancy kernels, stops being as interpretable. Feature importances stop being reliable or useful. And so this is one of the downsides to support vector machines. If you're you can either get high performance by using a fancy kernel like RBF and get these really nice fancy decision surfaces, or you can get interpretability. And in that case, you have to use a linear kernel, and that's going to come at the cost of performance. And so you sort of have this awkward trade-off. This begins to suggest why it is that support vector machines aren't all that useful, but there are other reasons as well. So I wanted to close this off with an overview of when you should use support vector machines and what are some of the pros and cons, and hopefully this will make more sense in light of what we talked about today. Okay, so the first point is, yeah, this question never has an answer. I mean, inevitably, I always stop myself short from saying that people should never use a support vector machine, but sometimes I almost want to say it because I have very rarely seen support vector machines be the best way to tackle a problem. I once went on Twitter to look this up, and I just found a whole bunch of different threads, and there was somebody said, why are support vector machines ever even used? And oh no, sorry, that's how this happens. I tweeted that question, and then somebody linked to this thread, and there was this whole exchange about the theory behind why they're not super useful, and then somebody came out of the woodwork and said, yeah, for this one application from 1987 data set or something, it turned out that they tried neural networks and they tried this and that, and support vector machines were the best one. So yes, it can happen. I would never deny that it can happen. However, it is not generally the best model to use. But again, good for you to know when to use it because, hey, job interviews. So with that caveat out of the way, support vector machines are good for sparse data. So when you have relatively little data and the dimensionality is really high. So NLP is a really good example of this. Why is NLP a good example of this? Well, there are a huge number of words in the English language. So, say 1 million words or so. So the dimensionality is really, really high. Many, especially if you're using a TF-IDF, if you're familiar with that, don't worry if you're not, but just, if you are familiar with TF-IDF, essentially what you're doing is you're creating one dimension for each word in your library. And anyway, the result of that is you're creating an ideal situation for support vector machines to do their thing, right? Because there's tons of opportunity for separability. And so that's one area where they do shine, and you will see support vector machines applied to NLP problems with relatively sparse data. Right, it's also good for high-dimensional data, as we saw, for separability. So when you start to combine sparseness and high dimensionality, usually that's a good time to use it. One of the reasons is that it's in a way, it's such a dumb algorithm. I mean, it really is just looking at like what's the bisector that maximizes the margin on both sides of my data. That's such a simple rule that it helps with the risk of overfitting. And so essentially, when you have high dimensional data, when you have very little data and it's high dimensional, you're at high risk of overfitting. And so you want to pick models that have a lot of bias and relatively low variance usually. Right. Okay. So there's an n-squared problem when you're calculating distances between points. So if you think about how do we come up with this bisector? Let me flip back to our first 2D representation here. How did we come up with this bisector here? Well, we had to do it through trial and error. We had to look at every possible pair of points and ask ourselves, like, okay, like, are these 2 points closest to the line? Are these two, like it looks obvious to our eye when we take a look at this problem, but what our eyes are actually doing, I mean, well, not actually because they're using convolutional net. Anyway, it doesn't matter. What a computer has to do in order to solve this problem in this way is it has to look at every pair of points and try to draw a line through them and see, okay, which line maximizes the margin on both sides of each pair of points. And that's a very time-consuming process because you're having to deal with pairs of points. And so if you've got 10,000, or let's say if you got 1,000 points, then, well, that's 1,000 squared, that's 1,000,000 pairs. So very quickly the problem explodes. And typically you're just not going to want to use support vector machines on data sets that are more than around 10 to the 4 samples, more than about 10,000 points. So this is yet another reason why the cases where you want to look at support vector machines are high dimensionality but low sample size, right? Because if your sample size is too big, then you're doing all this like n squared, looking at all these different pairs of points, and very quickly your computation is going to explode. Another thing, we touched on this just before this slide here, but if you care about interpretability, you want to beware of nonlinear kind of fancy kernels. Those kernels are going to make interpretability basically impossible, even if they will make your performance, your accuracy, or your F1 score, whatever you're measuring, a lot better. They do come at a cost of interpretability. And so this is not something to be thrown out lightly. For many business problems, if not most business problems, interpretability is important. You've got to be able to talk about feature importance. You've got to be able to point out which features deserve to be included and which ones don't, and so on, and explain why the model is making certain predictions. You can't do that when you start introducing some of these fancier kernels because it's really hard to say, oh, this sample was classified in this way because because I applied the RBF kernel and like e to the minus arm span squared plus height squared is less than this value. Like that very quickly just becomes very hard to express. So something to be aware of. And right, well, this is another important point, and it's something that's easy to miss out on. This whole conversation about support vector machines has assumed that our x and y axes are continuous numbers. Right? We've got points that are laid out all across the map, and then we draw a line to separate those points. But that's not the form that all data necessarily comes in. Sometimes you have, people who are categorized based on, I don't know, height as like tall, medium, and short, right? And like you might be able to project tall, medium, and short on an ordinal scale. You might say, okay, let's just call, short 0, medium 1, and tall 2. You might be able to get away with that. But what about, months of the year? Like it's not necessarily the case that like January should be smaller than February. Maybe there's a qualitative difference between months. Or colors, right? If you have blue, green, and red, like how do you map those onto a line? Very often you just can't. And in cases like that, your support vector machine simply won't be able to deal with that data. You need to deal with data that can be interpreted as distances. And so support vector machines are not the only kind of algorithm that suffers from this, right? K-nearest neighbors, same idea, right? It relies on the distance between points to be able to classify or do their regression task. And so you really want to make sure that you're keeping an eye on the kind of data that you're feeding into your model and making sure that your model can even understand that data, right? Another example actually is PCA. I can't remember, somebody raised PCA as an analog for this. PCA also can't deal with categorical variables. So trying to force it, and yes, you can sometimes force PCA to run on your categorical data, but that doesn't mean it's meaningful. And so that's one of the key things, is you've got to recognize what the limitations of your algorithms are. And because support vector machines do have, I would say, quite a few limitations. I mean, when you start to add this up, you're looking at, okay, we can do decently at high dimensional data that's pretty sparse, but we can't deal with large amounts of data. We throw away interpretability pretty easily, or we have to sacrifice performance, and we can't use categorical variables. That's a lot of hits to take, at least in my view, when it comes to the robustness and generalizability of this class of model. So this is sort of why you're not seeing them used nearly as much nowadays. But anyway, it's good, I think, to be aware of some of these limitations, because they will come up during interviews too. Are there any questions about any of the support vector machine stuff? I could pick on some folks. Wissam, did you have any questions? Assuming you can speak, you can write in your questions too if you want. Cool. Laura, just to circle around to you, because you had a couple interesting analogies to flag. Do you have any thoughts or questions? Oh, sweet. Okay, great. All right, looks like everyone's good. Everyone's good all at once. Okay, great. Well, let me know, as always, if you have questions to follow up on this stuff. This is basically the end of what I have here. Play around with these in scikit-learn too, and check out feature importances. Convince yourself that you understand how to do feature importances for support vector machines. I want to sneak one last quick observation in here, actually. One thing that you'll notice if you've actually been to the office hour sessions that we've done on decision trees, so decision trees and support vector machines, a lot of different models have their own almost custom feature importance sort of ways of gauging feature importance. So in the case of a support vector machine, right, it's like the slope of this line, roughly speaking. With a decision tree, it was like the number of times that a given question was used, or a given feature was used to split the data. These kinds of feature importance measurement strategies are usually the ones that are by default associated with that model when you train it in scikit-learn. So when you do model.feature underscore importances underscore in scikit-learn for a support vector machine, this is the strategy that it will use. And likewise for decision tree, likewise for logistic regression. Not all models come with a feature importance score, because not all models are interpretable in terms of feature importances. But the fact that these are essentially bespoke feature importance measurement strategies means that you can't apples to apples compare feature importances that you get from support vector machines to feature importances that you get for decision trees, for example. Because they are born out of a fundamentally different kind of analytical process. And so it's important to keep that in mind. I sometimes see people playing around with feature importances and trying to say, oh, I'll, or they'll get really shocked. I did my analysis using an SVM, and my feature importances showed that height is the most important indicator of athletic performance. But then I tried the same thing with logistic regression, and it turns out that something else is. That can happen, and it's just because different machine learning models end up looking at the data in different ways, and so they end up catching on to different things. So it's for that reason that I usually recommend, if you're going to do feature importance, that you use what's called permutation feature importance. You can look this up. I think I've spoken about it before, but I'll write it out here: permutation feature importance. This is a much more robust way of doing feature importance. It's a little bit more comparable across different types of machine learning models. Still, it's not quite apples to apples, but at the very least, it's not bespoke. So you're not using some hardwired feature of the structure of your SVM in order to make your importance measurements. You're using anyway something more generalizable. So if you want to look up permutation feature importance, it's a good thing to have in your back pocket. Other than that, I think is it